the area of a circle and you read pi, then all the threads, copy from the constant memory pi, it gets cached. So the first thread calling it is going to be an expensive call, but all the other threads, when they use it, is going to be cached. That's right here on the chip. And for the texture is the same. However, those 4 gigabytes, they are not cached, and there is a memory bandwidth large, very large. If you look here, if you look at what Intel has, is about the latest generation is about 32 gigabytes per second, and this here is 1 or 2 gigabytes per second. It's really, really high. Here is another picture. You have, this is block 1, and it has its own shared memory. It has its own registers, and in this block you have a number of threads. The thread has local memory, and the thread has access to the global memory, constant memory, and texture memory. To the global memory, you can read and write. Constant memory, you can only read from it. Texture memory, you can only read from it. Although there are tricks you can write into it, but it's something else. Now, local memory, it sounds local, but it's not local like in the sense that it's very short access time. It's local, it means that it's on the, it's local to the thread. In reality, it's like overflow. When you overflow the number of registers and data needs to be stored somewhere, it actually gets stored in the global memory, in the 4 gigabytes. So you don't have any control, you don't know that happens, and all of a sudden the code slows down a lot because, the overhead to get data back and forth, move data back and forth between thread and global memory is very, very high compared to moving it back and forth between registers or shared memory. So local, if you read the documentation, don't be misled by this concept of local memory. Stay away from that. Avoid that. So each thread, it can read and write registers. It can read and write shared memory. It can read the constant memory. It can read the texture memory, and it can read and write the global memory. The host, what it can do, it can push data down into the global memory. It can push data into the constant memory, and it can push data into the texture memory. So that's what it can do. I already told you the texture, constant, and global memory are persistent across kernel calls. So that's a nice thing. How fast is the memory access? So register, that's dedicated hardware, it's super fast. Shared memory, almost as fast as register. Local memory, local sounds local, but is actually in the global memory, very slow. Global memory, always very slow. There's no cache for that. Constant memory, it can be very slow, but it can also be very fast. If it's cached and everyone accesses at some point pi, then it's super fast. Texture memory, the same like constant memory, and the instruction memory, that's cached and that's invisible. You don't have any access to it. It's 4:15. If you want to leave, I'm going to keep talking. I like to talk. Very rarely people listen to. I don't teach this semester, so I kind of miss it. So I'll keep talking here. It's Friday. It's 4:15. If you want to leave, feel free to do so. And I should have told this 60 minutes ago. If you have questions, ask me. Stop and ask me. But it's not too.
Quick question.
Yes.
You said you're not teaching it this semester. Are you planning to teach it again next semester? The class.
The class.
Yeah.
I taught it in 2008 in fall.
Okay.
Next semester I'm going to teach a 700 level class, but it's not on this.
Okay.
Actually, it has about like 3 or 4 weeks about this and OpenMP and MPI, but I don't think that it's worth taking the class for that, unless you do dynamics and stuff. It's computational dynamics.
Okay.
So here is a comparison just to see how things have evolved. This is the latest GPU card, and this is the generation before it. Device memory, it went up from 1.5 to 4. Multiprocessors from those SMs. It used to have 16. Now it has 30. I think I told you 24. I was wrong. It has 30 cores, 128. Now it has 240. Shared memory same. Cache for constant memory same. Here the registers doubled, and the number of threads per block the same. Same. Warp size 32. Constant memory 64-bit. So NVIDIA is very aggressive about this, and I think that next week they're going to they have this NVIDIA conference. They're going to announce the next generation, the new GPU, and I heard it is going to be very impressive, and they are going to cut the difference in overhead to go to double precision in half. So double precision will be about twice the price that you pay for single precision. Right now they say that it's 4 times. It's more like 6 to 8 times. Okay.
So you can do double precision operation.
Yeah, you can.
It's just slower.
It's slower. So very quickly about the model here. This is the model, and it happens, every time you call the kernel. First, you allocate memory on the device. Second, you copy something down into the device. Third, you invoke the kernel, which starts, doing crunching numbers. Fourth, the kernel finished, and then supposedly some, useful information was generated. You bring it back. That's the end of the day. That's what happens time and again. Okay, sometimes maybe you don't allocate memory because probably you want to do that once, but then you keep copying data down there and retrieving data. Okay. How do you copy? So this is CUDA support. It says CUDA malloc. It's just like pretty brainless. It's a malloc on the CUDA device, and at the end you say CUDA free. It just releases the memory. Then you have a called CUDA memcopy, which copies data down into the GPU. It requires some parameters like pointer to source, pointer to destination, number of bytes copied, and the type of transfer. It can be from host to device, from device to host, device to device, and so on. The connection is a PCI Express 2.0. Basically 8 GB by second. So this is the umbilical cord linking the GPU to the CPU.
Quick question.
Yes.
So if it's 8 gigabytes per second each way, will it asynchronously copy if I want to copy one thing down and pull the other result back up?
Yep. It can do that. Or you can compute and it can copy.
Copy more.
Right. Except you have to be careful not to step on the memory that it reads right.
So you leave some allocated that it's still working on.
Exactly.
Allocate some new memory to stuff in. Alternate.
Yep. And then here it says you copy from memory from the host to device, and then you call the kernel, and at the end you copy from the device to host. Okay, very quickly, I'm going to talk about this because I want to also show you some animations and some benchmarks that we obtained with CUDA. Very, very quickly, what does this resource management mean? It means that it's a way to gauge the extent to which you use the hardware. Remember, I told you that an SM can handle the best case scenario 32 warps. Okay. Now, why do you care about that? Because the more warps you have, the more blocks and threads can get executed by one SM. The more you have, the better chance you have of not ending in a situation where the scalar processors are data starved. Okay. Because if you have many warps, one hits a read, go away, the next one comes, execute, you hit the read, go away, I grab another one. If you only have 2 warps, okay, if you have a block that has 64 threads, okay, and that block uses a huge amount of shared memory, okay, so what happens is that you have 2 warps, and if they both hit a read, then they are waiting there for the read, and the SM is idle.